In this exercise, we'll deal with the Lie group SE2. It is a group of 2D rigid transformation. So we will write it under the form of a matrix, so that we'll have a matrix Lie group. It will be more comfortable to compute with the computer if we use the matrix notation. So for the first question, we have to show that SE2 is a Lie group. So we can understand that under the representation of a matrix, we have the rotation part here and the translation here. So the rotation and the translation. T is a 2 vector and R is a rotation in the plane. So what it represents? If I have a robot, for instance this robot, like this, the pose of the robot, I mean the position of the center but also the orientation, can be represented by a translation vector T and a rotation R. But we have to understand that there is an order. We have the translation first and then the rotation. And this may bring some problems, as we'll see later, and this is why we'll need the Lie group framework. So here there is different way to represent this kind of object, but the way we have chosen is a matrix, so that we'll have a matrix Lie group, so that we'll be able to compute, to use tools such as the logarithm or the exponential. And this is immediately done if we use the matrices. So how I can prove that it is a Lie group? So if I have a Lie group, I have a group like this, G, and I have an operation multiplication. And I have to show that the multiplication is closed. I mean, if I take here, let's say P1, an element of the group, and P2, an element of the group, I will have the same form. So the rotation part will be defined as follows, and here it corresponds to the translation, so it can be easily checked. So the new element, P equal P1 times P2, also belongs to the group. It is also the same for the inversion. Or if I have an element of the group, let's say P1, then P1 minus 1 has also a rotation part or translation part, the one here. So it is easily checked. If I multiply this matrix by this matrix, I will obtain the identity. I also have to check to have the identity. So the identity corresponds to identity, so 2, 2 matrix, 0, 0 here. Here the translation will be 0, 0, and the 1 will be here. So the identity also belongs to the group. Now what is important to have a Lie group is that the multiplication and the inversion are both smooth functions, which is the case here. So I have shown here that the set of a matrix represented by this forms the Lie group. I also note that when P1, P2, P3 equal to 0, 0, 0, then the matrix P corresponds to the identity. So identity is an important part when we use Lie groups, because it is the place where the corresponding Lie algebra takes place. Question number 2. Using the derivatives around P equal to 0, I have to find the associated Lie algebra. So let me recall that here I tried to represent the set of matrices. It is 3-3 matrices, so it will correspond here to R3-3. I represent in a Cartesian form like this. And among all these matrices, some of them have this form. So R belongs to SO2 and some other not. So I will represent, let's say like this. I don't know how to represent it. I represent like this the manifold corresponding to SO2. So if I take a point here, it corresponds to an element of SO2. So to a rigid transformation in the plane. One of these points here, let's say this one, corresponds to the identity. And the identity is obtained for P equal 0, 0, 0. Now to have the corresponding Lie algebra, it corresponds to what happened in the tangent plane around the identity. So what I will have to do now is to linearize near to the identity. So I mean to linearize around P equal to 0. So in this case, near 0, P equals 0, or if you prefer, near P equal to identity, then the matrix P, which depends of P1, P2, P3, will be something like, so cos P will be 1 for the cos. Here it will be minus P3 due to this. P1, here P3, here 1, P2, 0, 0, and 1. So it is a first order approximation of P near to the identity. So it means that I will have 3 generators here. The first generator will correspond to the derivative of P near with respect to P1 near to the point 0, and it will be 0, 0, 1 due to this, and everywhere 0. So it is the first generator. The second one will be with respect to P2. The P2 occurs here, so I will have 0, 0, 0, 0, 0, 1, 0, 0, 0, and for the last one, with respect to P3, it will be so P3 occurs here and here, so I will have 0, minus 1, 1, and 0 everywhere. So I have 3 generators. This one will correspond to E1, E2, E3. As a consequence, the Lie algebra corresponds to the Cartesian space here. The identity here is here, and the generator E1, E2, and I do not represent E3 because I have here a two-dimensional representation. And these vectors have a correspondence, let's say here and here. It will be the image of E1 and E2 by an application which is the exponential. So recall that I link the two of them by the exponential or the logarithm. So this space is linear, and it is quite comfortable for me to compute in the tangent space, so in the Lie algebra. But here, to handle elements of SO2, I will use the matrix. Since I use the matrix representation, I can also use the multiplication of matrices because I have a matrix Lie group. If I take an element omega in the Lie algebra, so omega, let's say, it will be something like P1 E1. So here it is P1, P2, so plus P2 E2 plus P3 E3. It will be mapped thanks to the exponential somewhere here in SE2. So it will not be inside the tangent plane. So this element here, I will call it P. P will be the exponential of omega, or so of P1 E1 plus P2 E2 plus P3 E3. And this will not be equal to exponential of P1 E1 multiplied by exponential P2 E2 multiplied by exponential P3 E3, because these matrices has no reason to commute. So it means that when I use this representation, then it will depend on the order, so I cannot commute the computation, whereas here with this representation, the rotation and the translation we try to represent are performed simultaneously. So there is no problem of commuting, of problems when we commute the computation. Question number 3. We now consider a Dubins car, and the Dubins car has 3 states, x1, x2, x3. x1, x2 corresponds to the position of the center, x3 corresponds to the heading, and of course the state vector is a pose, so the position and the rotation is called the pose, and can be represented by an element of SE2. And then from this we want to propose a way to simulate, to integrate these equations. Okay. Here I have the Dubins car. So the Dubins car can be represented like this: x1, x2, the position of the center, the heading will be x3, and the state x1, x2, x3 corresponds to the pose, and it is an element of SE2. So it can be, for instance, this point here. Now, what we have when we have a Lie group, so here it is the Lie group here. Here it is a corresponding Lie algebra, so it will be SE2. So it is here the algebra. And when I move here, when I have a trajectory, when the robot is moving here, I will have a trajectory here and SO2, and I can only see what in the Lie algebra I can only handle the computation around E identity. So when I move a little, let's say here, it moves inside the Lie algebra. So it corresponds to what happened in the local frame of the robot. We present like this, the local frame. And I have a formula that that we have seen in the lesson for the rotations, and it was for the rotation. I recall that when I move like this, it was SO3, but of course here it is yes, it was SE2, but the formula is the same. And I recall that we had something like the rotation at time t plus dt is equal to the rotation at time t multiplied by exponential of dt multiplied by omega, so the rotation vector. So here it is in the Lie algebra, and it has to be represented in the local frame of the robot. So when I say this, it means that I am near to the identity. So if I apply this formula in our context, I will obtain, not this one, but P at time t plus dt is equal at the pause at t multiplied by exponential of dt multiplied by the motion, so the motion of the Dubins car in its own coordinate. So so I have to look at this, and I can see that when I move E1, I will move with respect to this direction, and it will correspond to E1. So when I change this one, I will move with respect to E1. So here it will correspond to this direction, and here this direction, and I will transport here, and I will move with respect to some direction like this. When I move U2, then I will move with respect to I will move the heading, so it will be E3. So as a consequence, I will have here U1 E1 plus U2 E3. Question number 4, we still consider the Dubins car. We assume that U1 is constant and is equal to 1. The same for U2, and we have an initial condition. And we have to use different approaches to compute the solution. So the exact solution, which can be computed easily, we'll see this. Then Euler integration scheme, and then the exponential integration scheme, and we'll try to compare all of them. So we'll take a time t between 0 and 6, and a sampling time which is very poor, but it's just to see the inaccuracy of the methods. And the sampling time corresponds to 0.5, which is very poor sampling time. I have here my Dubins car. Okay, we'll present here the Dubins car. And the initial condition is like this, is one here, and 0 here, and the heading is like this. Okay. So we understand that the car will turn left, so due to U2, which is equal to 1, so it will correspond to the direct trigonometric sense. So it will turn like this, and it will perform a circle. It can easily be checked that the true solution is a circle, so it will correspond to x1 of t equal cos t, x2 of t is equal sine t, and the heading will increase linearly, so it will something like this one at time 0 plus t. So it is a true solution, the exact solution. I have here my program which uses the library, the package rublib. dt is equal to 0.5, time is between 0 and 6. I initialize the scale of the figure, and I will propose the following procedure to draw the picture, and it is a result. So we see that here it is what happened at time t equal to 0, and here at time t equal to 6. So here it will be t equal dt, here t equal 2 dt, and so on. Okay. I have here implemented the true solution, which is given here, and here I draw the robot at the corresponding pose in green, and here it is the size of the robot. I will run the program. I'm here, I run it, and I get this. I will now integrate with the Euler formula. So I recall that the Euler integration scheme is as follows. The state at time t plus dt is equal to x at time t plus the sampling time dt multiplied by f of x of t u of t, where this corresponds to f of x and u. Here correspond to x dot, and if I do this in my context, I will obtain this formula. Okay. I will implement with Python. Okay. And I can see here I have a Euler simulation function which has input the initial condition and u1 and u2. The initial conditions are given here. Okay. And u1, u2 correspond to this, because I recall that u1 is equal to 1 and u2 equal to 1 also. Okay. So what we do, we draw at each step the state. Here I integrate here using this formula, Euler formula. Here I switch to Python. This is my program, and I will also in the same time first draw the truth, just to see the difference. If I do this, I obtain this, and we can see that there is a big difference between the truth, green, and the blue, which corresponds to Euler. For the exponential integration of the Dubins car, I need first to have a correspondence between the pose. So the pose will correspond to x1, x2, x3. So here is a small p, and here it is capital P, and I did a correspondence between the two of them. So here, of course, I will have x3, x3, x1, x2, x3, x3. Oh, it is given by this operation. To go from here to here, it will be the pose function, and to go from here here, it will be the inverse pose function given here. Okay, so I need to implement the generators E1, E2, E3 given here. So they generate the Lie algebra. Then I will propose this following simulation. So the simulation is based on this operation, which is given here. So this, this corresponds to dt times a, where a is defined here using the generator. I draw the tank, and I need the inverse pose to be able to use the function draw tank as programmed in rublib. So what I will do, I will first, for the comparison, simulate the truth, then the LR, and then the Lie. And we'll see that the exponential simulation, the exponential integration is very accurate, so it will superpose with the truth. It is why here I put a size just a little different so that we can see that it is very similar. So I will run this program. The truth, the layer, and so the truth is in green, and we can see that it overlaps with the red, and the red corresponds to the Lie integration or the exponential integration. The blue is a layer, and we can see some big differences. But if I put the exact size for drawing the car between the truth and the exponential integration, that I would obtain a perfect overlap between the two, and will not see anymore the green cars. So the consequence is when we have to integrate Dubins car, or for dead reckoning, if we have need accuracy, such that when we have inertial units or things like this, it is important to use the exponential integration. Question number 5, it has nothing to do with the Dubins car, but we have to find a path in the SO2 between t equals 0 to t equals 1, such that the initial pose corresponds to P0 and the final pose equal to P1. Each of these poses are associated to some state vectors. Also, it's not anymore state vectors since we do not use Dubins car anymore, but it will correspond to the pose -1, -1, -1, and 1, 1, 1, respectively. So I will recall the interpolation formula. If I have on SE2 here P0 and P1, I want to find a path here, so P of t, and it is what we call interpolation, and the formula is the following: P of t is equal to exponential of the logarithm of t times P1 times P0 minus 1 multiplied by P0. So I will try to explain this. So here I have some kind of vectors like this, and this vector corresponds to P1 multiplied by p0 minus 1. So this vector has a correspondence. It is a vector which is when p0 and p1 are close, it corresponds to the identity. So we can understand that we have some kind of representation here in the green plane corresponding to the Lie algebra. I represent like this vector as a correspondent here. And here it is a logarithm of, let's say, p1, p0 minus 1. And due to the t we have here, start at, for t equals 0, we start at 0, or identity, there is a correspondence, and we finish here at this vector. Now we come back with the exponential, and I obtain here some kind of path near to the identity. And we'll have to move this path to start at p0. It is why here I have to multiply at p0 by p0. Okay, so I propose the following Python program. Interpolation between p0 and p1. Here I use the formula. I build my matrix A, given here, that will be multiplied later by a moving t. And I use the exponential to find here in SE2 the corresponding path. Then I draw the robot, and I call the function here to interpole between this pose to this pose. This is my program. I run it, and I obtain here the path. Of course, here I have drawn a car, but it has nothing to do, it's just to represent a pose, because it's a path which has nothing to do with the Dubins car, but it represents a path moving from one initial pose to one final pose.